Okay, so we welcome back to this final lecture of this course, and we try to continue the proof. Maybe as I said, I will not do a our calculation. So, but if you want to really to learn, it's better that you work out the proof and all the technical details. So, we have proved that in the last class the trace is an h half function. Now we want to show that it is only the h half functions. That means the trace of gamma naught is precisely h half. So we will prove the other inequality which we state here. Okay. So this is the inequality. So you start with an element in h half of Rn minus 1, and then we are going to extend. We extend h. So we will quickly do that. Once you go through that proof, you will see that it is very natural. So we extend h x prime to u or x prime xn. So we want to define u x prime xn, and in such a way that when you put xn equal to 0 u, this we will do by Fourier transform on Rn. This is Fourier transform is very useful to extent, because because of this bijection and all that you can recover it back. Okay. Fourier transform in Rn minus 1 only in the x prime variable is enough, because once you know Fourier transform you know the function uniquely it determines. So what I will do is that, so only by, so I will define the Fourier transform of u before defining u. So I will do n minus 1 Fourier transform. Xn is a parameter at this stage. So I will have u tilde of psi prime xn, and which should given a restriction. So it should be at the boundary h tilde, you see, and then at this stage I put a very nice exponential function. So that very smoothly it will change 1 plus mod psi prime xn. This may not be the only way, because there will be different extensions, but you see if you put xn equal to 0, this term vanishes. So you get u tilde of psi prime, this is immediately implies u tilde of psi prime xn psi prime 0 is equal to h tilde of psi prime, that implies by uniqueness u of x prime 0 is equal to h of x prime 0. So that part is we are cleverly done. So that is already done. So you do not have to worry this one. So this is the Fourier transform in x prime variable. Okay, that is it. Now we want to compute this one, right. So this is defined for, of course, xn positive, otherwise that will be a thing. And now extend, so you go to u in Rn plus. So so u is defined, keep that in mind, u is defined only in, that is what we wanted, but then there is a technical difficulty. This is the problem, Rn plus only, you see, it is not defined thing. So but we still extend u by 0, extend u by 0 to all of Rn. The problem is that this extension, so I will denote by the denote it by u again. Okay, denote it by, because now I do not want to use u tilde, denote it by u again. The problem issue, u need not be in h1 of Rn. So you do not get, because we do not know the boundary values of u. So but then the trouble is only the extension at the xn direction. So you will not have problem of proving its derivative up to n minus 1 in other directions. Okay, other directions if you look at it, you already defined. So this extension only this xn direction problem. So, you will have the dn of u, di of u will behave nicely for all I 1 less than or equal to I less than or equal to n minus 1. So, di of u we expect u to be in L2 for up to n minus 1, but dn of u need not be. Okay. So, you have to do that one. So, therefore, it is not possible to prove, it is not possible, everything is in Fourier terms, possible to prove 1 plus mod psi square half u hat in L2 of Rn. This is not possible. So, first you have to understand these troubles. Okay. So, what we will do, so you let me write down the u hat of psi. So, let me compute some computation. I will not do all computation, as I said you can do this u hat of psi. I will just write down because I do not have time. So, you just write down the definition. So, this is your hx psi prime 1 plus mod psi prime plus I psi a. Okay. This you do it as a small exercise. Write down just the definition, integrate. Okay. Because you integrate except x and variable. Okay. So, you can do that. So, that is not an issue. You can write down because you know u tilde. So, you are comparing, basically you are writing down u tilde, u hat in terms of u tilde, and then you prove. Now, you take let 1 less than or equal to I less than or equal to n minus 1. Okay. So, this again a bit of a calculation. So, you will have di of u hat. So, all these again I told you these constants may change, these constants, okay, depending on what your notation is. Okay. So, therefore, u, this is only this we expect. Okay. di of u is in L2 of Rn plus, okay, that we expect because nth variable is the problem. We if you are not convinced, we are anyway proving it. If and only if this you know u hat di of u hat, okay, is in L2 of Rn plus. Okay. And this is equivalent to that one 1 plus you this one you write down in terms of psi a u hat, this use this so you will get 1 plus mod psi prime, you see psi n will not come there, a prime modulus of u hat of psi square and is finite. That is what you want to prove. Okay. So, you will get that one. Okay. Of course, this. So, this is what you are proving. So, okay. Rn plus. You want to show that u is in H1, right, of Rn plus, and this is easy. So, you compute this one 1 plus mod psi prime square u hat psi square d psi is equal to some constant will come in my thing. I think the constant is pi, but then it will be Rn minus, okay, 1 plus mod psi. Do the computations again and again. I am repeating half h tilde of psi prime square d psi prime. So, you see you converted the Rn integral, Rn or Rn, yeah, both are same, this one to this one, anyway u is 0 outside. So, you see you converted this integral to this one, this is nothing but some constant pi, the constant is pi, nothing but your h till h in h half of Rn minus. That is what you have square. yes, square here, and this is given to be finite, so this is finite. So this proves, this one proves that. Now we want to go to the next one, that is again the standard tricks you apply. So you look at dn of u, the last part. So dn of u for the entire extension you can't prove it. So we take it only on the upper half part. So it's L tilde psi prime xn equal to dn of u tilde, okay, psi prime xn, correct. Yeah, psi prime, this is for xn positive. Okay, I am doing only for xn positive in this case, because okay. Yeah, that is fine, because that is not a problem, because this is the extension, and this you can compute to be my, I have made my computations here, psi prime into u tilde of psi prime x. I can do this. If there is anything, check it. If there are mistakes, check it. Okay. And then I am not taking the extension of u and then taking the derivative. Rather, these are all small tricks you would have learned anyway in the Sobolev spaces, distribution theory, etc. You take the Tn on the upper half plane, take the Fourier transform, and now extend dn of u by 0. That is fine. So there is a operation difference. Extend dn of u by 0 outside R. That is fine, because in the L2 setup now you have to prove that your dn of u is in L2 of Rn plus. Okay. So that extension by 0 will retain that, okay, L2 spaces. And I as I said again, solve some exercises, because I want to tell you few more other things. So I will keep here now. This is about the dn of u, its hat now. Keep that mind, dn of u extended by 0, I use it now. The new dn of u is dn of u. So I am extending dn of u if xn positive, and then I do not want to use a notation of tilde, dn of u tilde, that is what I am saying, if xn less than 0. So I use, when I say I use the same notation, this is the meaning of that, I use that one. So this is the dn of u I am using here. So its Fourier transform you can compute it now. I will again do the computation, and I hope all my computations are correct. If not, correct it. Of h tilde of psi prime, you see, I said it is a bit delicate proof, delicate but very beautiful and cute proof, which I say sometimes. It is not a kind of a dirty proof, it is a plus I psi n, you see, you get that dn of, and this can be computed, and this you can show that this is in L2 of R. These are all you can do, that is not a problem. If you want all these exercises, computations, so small computations you can do that. You can precisely write down everything and do this. Okay. All right. And we already seen that, so the third part is proved. So the proof of 3 is complete. Proof of 3, that is gamma naught of h1 of Rn plus equal to h half of boundary of Rn plus 1 is complete. The last part of the proof I will come little later means soon, okay, complete. But then I want to write down the trace map, more general trace maps. Okay. So suppose remarks, generalization. generalization. So suppose U is in H2, U is in H2 of Rn plus, okay. Then that of course implies U is in H1 and gamma naught of U is defined, okay. But du any variable, for example, for dn of u, for example, that is for example dn of u is in H1 again because u is in H2, okay. The problem is, you see, in this case the problem is on the boundary restrictions. How do you do that one? Here everything is fine, there is no boundary. So there is a normal vector in this direction, nu equal to 0, 1, etc. minus 1. That is a normal vector. Okay. So dn of h1 of omega, and you can basically define gamma naught of, I will put the some sign appropriately for the computations of the future. Okay. So you can restrict gamma. In other words, such maps with something. So there exists another trace map, trace gamma 1 of u, where the derivative will be restricted. Derivative is restricted. I am not writing, I am going to give it correctly, full restricted. So you get it. So if you take u in hm, you can restrict u, its derivative, second derivative, third derivative, till you get it n minus 1 derivatives. Okay. So you have trace maps for all that one. So that is the theorem. Okay, theorem, trace theorem, trace. Okay. And so I am going to write it. There exists a continuous linear map. Maybe I will write, so maybe write map gamma 1. This is in H2, more general I will write Rn plus everything to L2 of Rn minus, such that I will H that gamma 1 of u, maybe I will put a minus sign, because that minus sign is coming my normal. I told you, you do not have to have minus dn of u, minus dn of u at x prime 0 if u is smooth. You see. So I am basically what I am taking is that this is nothing but your normal derivative. You see, this is d by d nu of u, du by d nu for that direction, because all other directions do not come. So it is nothing but the normal derivative. So that is why I put the minus sign. You can put it without that. So you will get this is external. So it is a customary, generally in PDE people always use external normal derivative, outward normal derivative. You can use it inward and then you can write down all the equations. So more generally, okay, there are continuous linear maps. So let me write it together. Gamma is equal to gamma naught, gamma 1 up to gamma n minus 1. All these maps from HM of Rn plus to L2 of Rn minus 1. Of course, each one will be power n such that, so let me write down everything, such that, and 1, of course we restricted to that, you will get the continuous map. The main thing is that range of gamma is each time for gamma naught you lose what we call it a losing a regularity of half. This is the observation you have to make it in the trace theorem. When you started with u in h1 of r, you got the trace, the boundary is h half. That means more and more hr means it is more and more regularity. So, you lost a regularity of half. So, once you take a derivative and the derivative is taken, you already lost a one derivative, and then when you restrict you lose another half. So, each derivative that many will be lost plus half. So, that is a thing you have to use it. So, for gamma j you will have h. So, if you take a jth derivative, even the function itself by taking a jth derivative, that lost j derivatives, and then you lose half derivative of Rn minus 1, and then this is all your product, right, j equal to 0 to n minus 1 product. Okay. N minus 1, and 2 its kernel of gamma is nothing but your h m naught of Rn plus, the density part. Okay. Okay, so you have more general theorem. Now, so this proof is you do not have to prove separately because it follows the first part is proof. Now, come back to the previous theorem, the fourth part, part 4. Okay. So, part 4 what is to prove? To prove not for this theorem, the first theorem, the gamma naught of kernel of gamma naught is equal to h1 naught of Rn plus. Okay. So, one part is trivial. Okay. This part or whichever it is, part is trivial because one part I will state what is the trivial part. So, you see, if you have a V in dRn plus, be careful, okay, dRn plus, that means you are taking function with a support somewhere here. Okay. Then definitely V restricted to Rn minus 1 is 0 because that is 0, here you will get 0. So, dRn plus is contained in h1 naught because h1 naught are functions which can be supported by sorry, that is not what I want to say. That means this immediately contained in the kernel because kernel is 0. So, this implies dRn plus, that is trivial thing, right, Rn plus is contained in kernel of gamma naught. That is a trivial thing because you have a full 0 in that one. So, but this is a closed set, this is closed implies that its closure Rn plus closure with respect to h1 is contained in kernel of gamma naught. Okay. And this is nothing but your h1 naught. You see the closure in h1 is your h1 naught. So, that is trivial. So, the other part is complicated. So, you got to work out something approximations. So, to prove kernel of gamma naught is contained in dr not drn is contained in h1 naught. That is what what you need is integration by parts formula, integration by parts. So, let me state this is already proved in the previous classes. So, in this particular case, let me write down the integration by parts formula. Integration by parts formula, you can change the derivative to other thing plus a trace thing will come. But in this case the trace is only in the xn equal to 0. So, only the nth directional trace is there, the other thing you do not need it. So, you will get is the trace theorem, the trace theorem's integration by parts formula are v di of u is equal to minus di of v u for all uv in h1 of Rn plus. This is a trace theorem you have proved. Okay, I am just specifically write down this is for 1 less than or equal to I less than or equal to n minus 1. There is no boundary term, and integral u dn of u, the nth part, you will have minus dn of u or v dn of u, dn of v u plus, in this case it will come minus, that minus is coming because nu is minus. So, I have taken here minus gamma naught of u into gamma naught of v, that is in Rn minus 1. So, in Rn minus 1 your surface measure is nothing but your Lebesgue measure. So, you can write down dx prime. So, you do not need anything else because it is the flat boundary, this one. So, this formula immediately tells you something. If because of this one, if u is in kernel of gamma naught, that is what you want to start with, you see. If u is in kernel of gamma naught, the last term will not be there because gamma naught of u is 0. So, you get immediately integral of u di of u equal to v di of u is equal to di of u minus di of v u for all 1 less than or equal to I less than or equal to n, and this is the exact formula you need for the extension. So, if your gamma naught of u equal to 0, you can extend by 0. This is the extra boundary term, it will pick up when you extend by 0, it will only pick up the boundary values. Okay. So, if gamma naught of u equal to 0, the extension by 0 will remain in H1. So, you can extend by 0, that implies can extend u by 0 if gamma naught, if the trace value is 0, you can extend u by 0 to all of H1 of Rn to all of Rn to all of to H1 basically, can H1 of Rn to get extend to Rn to get H1 of Rn, the extended function. That is a first step. So, I am only giving the sketch as I said. Okay, I am only giving you the sketch of that. So, there are some few small things as I said, all this whatever I said just now, you just verify. Now, the idea is that I will give you the pictorial thing, you have to do it in few steps. What do you want? We need to approximate u, keep that, do not forget that, we need to approximate u by d are n plus 1 functions. That is the problem, right? So, d are n plus 1 functions. That is the whole thing. DRN functions you can approximate, but you want to approximate DRN plus function. So, now you have the extra thing given here is gamma naught of u equal to 0. This is the additional thing given to you. So, you can extend u by 0 here. Now, what I will do to get is that you just lift a little bit in this direction. So, you take this distance to be h. So, basically h is equal to 0 etc 0 some small h which goes to 0. So, do not worry, I am taking write it as a vector or whatever it is. So, it will move these functions and look at the translations. So, you basically what you do is that tau h. So, you have your u and now you have an extended function and then extended functions. So, you have tau h of u. So, I did not use again tilde here. So, now the u is, as I said, u is u if xn is positive and then 0 if xn is negative. The same thing, same philosophy I have used if you do not use it. And then this extended function if you use, you see the u has support here above this one, the u has support like here. You see, that is your support of u. But then if I take tau h of u, you see, oh sorry, so that is not the thing I want. If I take tau h, so you see tau h of u will have support here. This is the support of tau h of u, you see. So, if I take your tau h of u, the support of tau h of u, will be contained in set of all x prime xn with xn greater than h, you see. So, you have, and then you can actually show this tau h of u. So, there are a few steps, that is a few steps to be proved whether tau h of u will converges to u in L2 and then the derivative of tau h of u converges to u. So, you actually have to show that tau h of u converges in u in H1, okay, and then you have to smoothen it. So, you have to have a cutoff function, so and with compact support. So, there are few steps to do it. So, to do these steps first you basically show that tau h of u will converges to L2, then dn of tau h of u the derivative will converge, and then you use cutoff functions to make it compact support, and then you take your modifiers and convolve with it to get C infinity function. So, so these steps you have to do it, all these steps doing that, and there are few steps to be worked out for that. Okay. So, typically you get you choose everything some rho epsilon of n, convolve with it, then you have so I do not think I have time m, then you have cutoff functions, cutoff maybe zeta m, cutoff, modifiers, cutoff, and then you will have translation. So, you see u. So, tau h. H also we can write some hm, where hm goes to 0 as m tends to infinity. So, tau m will make it compact support, tau h will translate, so that when you operate with rho epsilon m it will not go out, you will get d omega functions. So, you can make everything epsilon m goes to 0, okay, hm goes to 0. So, you choose appropriately like that, m tends to infinity. So that even after convolution the supporter is in inside. So this you can see is in DRN plus. You see, that is what how you do it, and then you have to show that this converges to U, you see, in H1 RN plus. You can do that. Okay. Okay, so maybe it's time, but it's a last minute. You can do that. General domain, general, a couple of minutes, then I will stop. General domain. So you already seen that smoothness, smooth. Okay, d omega is smooth. This is already introduced, and basically smoothness tells you once the domain is smooth, you can extend things to a bigger domain. Okay, that is the whole concept. So different ways. So basically you can see that you can every point you can have a neighborhood. That neighborhood can be mapped to a small this thing. So that this goes here, this goes here, this boundary comes here. Okay. So once you do that, you know how to extend from functions from here to here, this point, and once you know that, you have extension. So the smoothness is defined. There are various ways defined, but some smoothness is essentially to get extensions. You can get extension, and you have seen that how density extensions are important in the whole analysis. So basically using these things, there is a way to define Hs of gamma. There may be defined, there is a way to define first locally and then define Hs of the boundary. This you have to understand, because once you have something, restrictions you already learned. Hs of omega you already learned in the previous classes, that you can restrict Hs of d omega, but you can come here and then extend properly. You can define Hs of Rn minus 1, okay, and that you can take it back to the boundary. So there is a way to define. With that you can define trace theorem. Let me not write everything. So you can write the trace theorem. So you will basically you will have a normal derivative nu, and then you will have d nu. So so you have all these L2 measures and things like that. So you have the trace theorem. What it tells you is that you can have trace theorem gamma naught, gamma 1, etc., gamma n minus 1 from Hm of omega to L2 of d omega, and if it is smooth, so the gamma naught of V is equal to V, gamma 1 of V is equal to d by d dV by d nu, etc. You can define gamma m of V, m minus 1 of V, n minus 1, m minus 1 of V is equal to d power the mth V by d nu power m minus 1 if V is smooth. So you see, you can do such things. V is smooth, and then you will also have all these range of gamma is equal to the product j equal to 0 to m minus 1 of h minus. All this will be useful in the study of PDEs. That is what I am writing, d omega, and kernel of gamma is nothing but your Hm of naught of omega. Okay. So let me not get into another page, exactly 12 pages I have defined. I will stop. So for example, this is already you have seen H1 naught of omega is, of course you need the smoothness of V, keep that in mind. V in H1 such that your gamma naught of V equal to 0 on d omega. Smoothness of the thing, you can have H2 naught, because we may use in the next class, is equal to set of all V in H2 such that your V gamma naught of V, that is V okay, gamma naught of V and gamma 1 of V is nothing but this is V equal to 0 and dV by d nu in the sense of trace equal to 0 on d omega. So H2 naught of omega is not set about V in H2 with V equal to 0. Both V and dV by d nu are 0. So with that you can have with this. So you see, you used the trace theorem in Rn minus 1 to prove that, but with the same thing you can get the trace theorem. Not trace theorem, what do you say, integration by parts. You can prove integration by parts in omega, because the whole Sobolev space started with the idea of proving that one. So I want to do a couple of things more, but I think I will not do. So whatever remaining, whatever needed, we will prove it in the next course. Okay, whatever is missing in our first semester course, this part 1 course, and if anything is needed to study PDE weak formulation of that, we will introduce it in the next course. And with this we will end the whole part 1 advanced PDE 1. Thank you very much for listening to the entire course. But be prepared to work out, spend time, do the calculation instead of just watching the videos. Just watching the videos will not benefit you much, but if you are already studied this as a course, watching will help you. If you are a first timer, make sure that you will also work out the details. Thank you very much once again.